temperatures. The rate at which an object emits radiation is called the power radiated. I'm going to call it P sub R, and the amount of power radiated by an object is given by the law called Stephen-Boltzmann law. And Stephen-Boltzmann law is a relation between power radiated by an object, the area of the object, and the temperature of the object. Alright? The law simply says the amount of power radiated by an object of area A maintained at a temperature T, that is Kelvin temperature, is given by P sub R equal to E sigma A T to the power of 4. Obviously, these two quantities, E and sigma, are constants. Now, E is a constant called the emissivity of the material. Emissivity. And E has values for all materials ranging from 0 to 1. If an object is a perfect absorber and a perfect radiator, that object has an emissivity of 1. If there is an object which does not absorb any energy or does not radiate any energy, its value of E is 0. For a perfect radiator, E has a value 1. And actually, a perfect radiator is called a black body. A black body absorbs all the radiations fall on it, and it emits maximum radiation at any temperature. A perfect radiator is sometimes referred to as a black body. So E is the emissivity of the material, and sigma is called Stephen's constant, which is determined experimentally, and it has this value, 5.6703 times 10 to the negative 8 watt per meter squared per Kelvin to the 4. Now, these values will be given to you in a problem, so you don't need to worry about it. So, the power radiated by an object of area A maintained at a temperature, absolute temperature or Kelvin temperature T, is P sub R equal to E sigma A T to the power 4. Now, this is a measure of the amount radiated by the object. At the same time, the object also absorbs energy. The amount of energy absorbed by an object depends on the temperature of the surrounding. You see, if I stand in a very warm room, I will be absorbing energy. If I stand in a very cold room, I will be radiating energy to the surroundings. So if T0 is the temperature of the surroundings, then the power absorbed by the object is given by PA equal to E sigma A T0 to the power of 4. So you can see power radiated depends on the temperature of the radiating object. The power absorbed depends on the temperature of the surroundings. Alright, therefore what is the net power radiated? You see, the net power radiated is the total power radiated minus the power absorbed. Is that right? So I can now write the net power radiated is this minus this, and that will be E sigma A times T to the power of 4 minus T0 to the power of 4. Okay, let's do a problem. Calculate lambda max for a human black body. Well, what does that human black body mean? Well, it simply means assume that human body is a perfect radiator. Assuming the surface temperature of our skin is 33 degrees Celsius. What is the equation for lambda max? Wien's displacement law. Lambda max is given by 2.898 millimeter Kelvin divided by the temperature in Kelvin. So in this case, the temperature has to be converted to Kelvin. That will be 2.898 millimeter Kelvin divided by 273 plus 30 is 306 Kelvin. That is 9.47 times 10 to the negative 6 meter. That is the wavelength of the maximum intensity radiation that is emitted by human body. And do you remember where does this radiation come in? It is in the infrared. So we emit infrared radiations, heat radiations all the time. Okay, let's do another one. The heating wires of a 1 kilowatt electric heater are red hot at a temperature of 900 degrees Celsius. Assuming that 100% of the heat output is due to radiation and that wires act as black body radiators, it means the value of E equal to 1. What is the effective area of the radiating surface? Well, we need to find A, the area of the surface. Let's pick our data. The power radiated P sub R is 1000 watt, 1 kilowatt. The temperature of the radiating object, that is the hot heater, is 273 plus 900, 1173 Kelvin. The temperature of the surroundings is 293 Kelvin. Sigma we know, the Stephen's constant, and E is given to be 1. It's a perfect radiator. What all we need to do is write down the equation for the net power radiated. The net power radiated is E sigma A T to the power 4 minus T0 to the power 4. And we know all these quantities except A. So solve for A. A will be equal to P net divided by E sigma times T to the power 4 minus T0 to the power 4. And now put in the values of all those numbers in there. Right? And that's equal to 9.4 times 10 to the negative 3 meters squared. That is the area of that heating wires. Okay. Well, we have now gone through briefly discussing the methods of heat transfer, and this brings us to the end of Unit 2, where we discussed, well, briefly thermodynamics. Now, once you come to the end of a unit, you must be getting ready for the exam at the end of the unit. So please go through that practice test and make sure you understand all the concept. All right? And then do test 2. And I will get back to you with next lesson in Unit 3 later. Okay?